my name is Brandon Rodriguez. I work at the Jet Propulsion Lab for NASA. I'm really excited to talk to you guys about a couple things. I actually really saw a lot of my talk in the premise of this kind of tinkering phase, right? This really speaks to me quite a bit because for a long time now, I've known guys like Nick. I've worked with them, and he's an amazing teacher, a great classroom teacher, who has kids that aren't afraid to fail. And I'm a high school teacher by trade, and by the time they've come to me, I don't have that luxury. So when I see a lot of this equipment, I think, man, I have so many kids that would love it, but I need to train them on how to understand that there's no blank, there's no right answer, they're not going to be graded, with a number on the top. And that's kind of what I was hoping to talk to you guys about today. My role over at NASA Education is teacher-facing, so I go out to schools, I do a lot of outreach, and we host a lot of cool things like workshops at JPL where you guys can come out and do activities with us, where we'll kind of test some of these amazing resources and see how can we take these to classrooms. We have a ton of curriculum online. Everything's free, of course. You guys are taxpayers. You pay for NASA, so it's all available to you. So if you're in the area, you want to come out and see some of what we're working on, let me know. We'll chat about it. You can see at the bottom of this picture, we've got, this is us doing a workshop very similar to some of the things you can see here. This amazing rover over here that's been constructed is like an open source 3D design, and they use the PyTop computer on it. We're actually doing something similar here. That picture is a 30-foot by 30-foot topographical map of Mars that you can borrow and pilot around it. Use a color sensor to make sure that they stay on the high land versus the low land, stuff like that. Really, really neat stuff. But it's actually not in my NASA function that I'm here today. I really want to talk more about the teacher side of this, which enjoys things like the resources that you can see on the web page. More importantly, free merch. We've got a ton of free merch. I tried to bring some stickers for you because everyone likes the NASA logo. But if you are a teacher and you want us to mail just like some class sets of stickers or posters for you guys, if you go to this website and click on that Educator resource section from JPL, we'll just mail you a bunch of free stuff. So take these amazing tools and put a little pizzazz, right? A little character on it, and make it a mission to Mars, right? And make it a cool space travel that will do these cool things with your imagination. Get your students really excited, not just about the process, but the narrative as well. So you'll see a ton of cool stuff, and I hope you'll check it out. I'll, of course, point you guys to resource, and I brought a bunch of free stuff because I just love to get it out of my car really more than anything else. Again, I really want to talk to you from the perspective of a teacher. So I am actually a high school chemistry and physics teacher for the last 5 years now. I still teach in the morning before going to work. I love the classroom so much, I wasn't ready to give it up, and JPL was very kind to let me teach 2 periods in the morning before I went into work. Here are my kiddos last year for the big eclipse. I'm sure everyone remembers. It was a really cool event. So basically you're just going to hear like proud teacher brags for the next 15 minutes. So again, as a physics teacher in a Title I school, my challenge is I've got kids who have never seen scientists. There are no scientific role models. There's no museums in these neighborhoods. So how do you get them excited about science? One really cool way is you get them kind of meeting them where they are. So kinematics is a tough pitch to get kids thinking about, man, let's calculate acceleration. So you get the cheerleaders and you get them to put a device on and they measure their acceleration in the X, Y, and Z. Now they're very interested, right? Now I just hooked 4 girls into physics that had no chance of caring about this in any other way. In addition, let's see, I have a bunch of students that are in band. So, doing things like around wave properties and stuff like that, easy connection, right? So I had my students actually build and film instruments, and they had to build a fundamental secondary and a tertiary wave and be able to capture it in slow motion, right? So you'll see different materials on each of the strings. Super cool. I also, as a quick background, have never given a lecture in my life without an activity, and I'm not going to break that trend now, despite the fact that it's short. So what I'm going to show you guys really quickly, you guys are going to do an activity for me. And again, it's so timely because I was in a middle school today, and a kid asked me, they like to try to get me. They think they're going to get the NASA guy, right? First of all, I'm not that bright. I just work there. But they all really get together, and they're like, we're gonna ask the question. So today's was, if there are so many stars in the sky, if there are as many stars as you say there are, then why is there nighttime? Right? There's, billions, right? Hundreds of billions of stars shining light. Why does it ever get dark? This is a 7th grader. I was at an 8th grade classroom, and this kid came in to ask me this question. He had clearly been thinking about it. It's a great question. So what you guys are going to do for me, just kind of like with people around you real quick, I'm going to hand out some balloons, if you would. Again, I'm high school, so there's no please and thank you. You're going to do it. It's so what I would like you guys to do as I come around, if you would be so kind, if you would blow this up to 5 to 8 centimeters across, just to get started for me, okay? Don't tie it off, just hold it for me at about 5 to 8 centimeters across. Did I get everyone? Is everyone good? Everyone got a partner-ish? Okay. Oh, really? This is, again, I am a teacher, so it's like dollar store. So, they're cheap. It's a very authentic situation, right? All right, next step. What you guys are going to, we're metric, we're scientists, please. Okay? Yeah, that's totally fine. Great. Have your partner or someone near you, I'll get you one sec. If you guys would do me a favor, I want you to draw just a little box and fill that box in on your, let's get you a darker one for red. Yeah, don't tie it off because we're going to need to change it. Yeah, draw a little 1-inch by 1-inch box on your balloon. Yeah, sorry, convert it. That's an important skill. Oh, sorry. Yeah, right, I know, huh? Let's get you a dark one. I'll trade you this pink one. And then we'll put this one on here. Perfect. And then this guy needs another one. Cool. Oh, you got a mark already. Cool. Perfect. All right. So 5 centimeters across, and then 1 divided by 2.54 inches on each side of your box, right? And it's not going to be nicely colored in. Can someone model excellence for me? Yeah, let's see this right here. Cool. Like so. Yeah, very nice, right? Perfect. Teachers in the room, right? Like so, okay? That's all I need, okay? Thank you. Now what you guys are going to do is I would like you to blow that up to about twice the size. Awesome. Can someone describe to me what happened inside the box? Is it the same? Is it different? It's faded, right? Is the box larger, smaller? A little bit larger, right? Cool. Now, again, if you're a super dork like me, you would know that the size change follows what's called the inverse square law, right? So as you get further and further away from a light source, if you can imagine you were in the middle of this balloon, right? And light is getting further and further away, the intensity of that light fades to the inverse square law. It's not equally faded as far as you go. So for example, Jupiter is 5 times as far away from Earth, from the sun as Earth is. So it has 1/25 the light, right? So this is the answer to the question, right? And this is why I have crazy things like balloons in my car, because when that kid comes up, I can try to tell him this. I can say, oh, just take 1 over the square of 5. That doesn't mean anything. But little just models, like little just tinkering models that you have ready, all of a sudden demonstrate why it's so dark. Now, this balloon we took from 5 to 10 centimeters. Now let's think about the vastness of space, right? So by the time that distant starlight hits us, it's expanded, it's spread out, it's faded to such a degree that we still have much, much darkness in the sky. Does that make sense? Cool, right? Just like a quick little model there. All right. Now, I love talking about this stuff to kids because they really want to know, I'm lucky, today was a lucky day, right? That's a good question. Really, they want to say, aliens, where are you hiding them, right? That's the question I get, right? And the best way to find aliens for these kids is in exoplanets, right? Exo meaning outside, like an exoskeleton. That's where we would find someone, a planet outside of our solar system. In fact, you can probably see something a little weird taking place on this picture. Can anyone ID it for me? Something's not right. Yeah, there's a little circle in front of the sun, and it's Venus. So Venus is actually passing between Earth and the sun here. Now, Venus is not an exoplanet, but this gets us to how we detect planets that are far away. So what we're talking about is a transit. So what we do is we look at these distant stars, and when a planet crosses in front, then some of that light is blocked out. We can track how much light is blocked out. That tells us how big the planet is. And how long it blocks it out tells us how fast it's moving in front of its star, right? So now we've just described a transit. Transit curves look like this. You'll notice that my picture makes it look like there's this giant drop, but if you look at the axis here, right, we're really talking about fractions of a percent. So we really need some high-tech devices. The problem when you look for exoplanets is that I make pictures that look like this. Those planets would be very easy to find when, in fact, they look a little bit like this. That makes it a little bit harder, and then it turns out the suns kind of look like this, and all of a sudden things get really, really difficult. So this Eye of Sauron little situation that you're looking at, this is how we actually look for transits. So here they are. So my cartoons make it a little simpler, but high-tech devices allow us to kind of look for those very small drops in light. This is what the real data looks like. This is also open source. There are a lot of really cool apps that let kids get the data from satellites as we find them and kind of tinker with it and say to themselves, have I found an exoplanet? Or is it a solar flare? Or is it a sunspot or something like that, which is pretty cool. Great citizen science. This is all, again, I'm going to trick you into math. This is all effectively Kepler's laws. So Kepler, a pretty smart dude, found out that the distance of a planet from its sun cubed was effectively proportional to the square of the period, the time it took to rotate around. So again, that's how we can figure out how fast is something moving and how far it is from its sun. We have a lot of cool activities on this, again, on the website, where we'll give you guys the real data, and kids will be able to extrapolate what crazy exoplanets are out there. This was huge because last year we found a solar system called Trappist that looks, in fact, very similar to ours, right? Several planets in the habitable zone, some too hot, some too cold, right? That's why you get that Goldilocks term. And this has really led to this explosion of planetary detection. So there are a lot of different ways that we look for planets. We can effectively use this transit method that I discussed. Now, looking at this from before, does anyone have a guess? What is a shortfall of the transit system? When would this not work? What was that? Yeah, beautiful, right? I need line of sight in 2 dimensions, right? I need the planet to cross in front. But space doesn't do me that favor. right? So sometimes I can't use this method. Maybe instead, I can use something like this, right? Now, turns out that Newton was a pretty bright guy too, and he found that gravity is a two-way street, right? A sun doesn't just pull on a planet pulls on a sun as well. And so you can actually see some movement in both species, and because of the movement of light, I can see red shift and blue shift, right, as it comes towards me or away from me. Again, my kids and kids I visit, they care about this because this is where we're going to find life. I need to know where those planets are. Now, my last thing I'll tell you guys is Newton's laws are not interesting to kids, right? F equals ma is not fantastic news to them. But the crazy stuff that's happening now, this is where they're asking questions. This is where they want to play. So the best way to find these crazy things out there is the fact that Einstein was right too, right? Space-time bends. And as planets move, or masses of great gravity move, all of a sudden, the light will bend around them as well. So you get things like this. What if I could see this gravitational lensing where light bends around a black hole as a galaxy passes behind it? That's what you're seeing here. So galaxy in the background, between me and that galaxy, a black hole. What a cool little effect here, right? Predicted years and years before we had this cool picture that we had today. Now, this is interesting to me, and my kids love to talk about this because I went to school as a chemist for a very, very long time. I learned that the periodic table is the answer to every single question. And then, now kids learn about dark matter. Every element that I thought was the answer, and there was this nicely organized routine, and it turns out none of that is correct, that the periodic table makes up 4% of the matter in the universe, and I spent 35 years of my life looking at 4%. So my last little activity for you guys is a quick discussion. If I have these two bottles here, try to mic it and hold, how do I know one of these has liquid in it? So here I have two bottles. We all know there's liquid in one of them. You can't say open it, you can't say drink it, right? First of all, you don't know it's water, okay? But how do I know that there's liquid in one and not the other? Beautiful, right? Kind of a callback to our gravitational lensing. Light moves through one of them differently than the other. Agreed. Anything else? Yeah, you see an air pocket. Maybe I should fill it up more. What else? The objects inside move differently, right? These are moving through some sort of fluid, and these ones just kind of bonk down to the ground, right? And it's the same case with dark matter, right? Dark matter is all around us, but there are these dense pockets, like you can see here, that allow light to bend around it. And in fact, we see these Einstein circles, even when there's no galaxies in between, thanks to dark matter. And you can even get some of these crazy things where you start looking at collisions and getting gravity waves, like was found in the Nobel Prize last year, right? Some pretty wild stuff out there. Now, again, the purpose of me telling you guys all of this today is not because I expect you guys to just run out and be like, every book on dark matter, please. But these are the questions kids are asking, and it's such an opportunity because there aren't answers yet. I know as much about dark matter as any kid in my classroom, right? I can't get out there. I can't touch it. I have no idea what it's made out of. We're going to explore together. Soon they will be the subject matter experts. And that we have that opportunity, like I was saying at the beginning. We're going to be wrong. We're going to be confused. And soon we'll be in that big sandbox where we've gotten over this idea of what's wrong and what's right. Let's model it a little bit, maybe something like this, where we build little gravity wells with the kids, right? So you can see I've just taken some cloth and some wooden marbles. The wooden marbles orbit the metal marbles, and they hit this dark matter in the middle, right? So we can do some really, really cool stuff with basic tools before the kids can maybe move on to these big, tough questions. Again, tiered out, like you heard, starting with this kind of, we're all on the same page, next we're going to tinker, then we're going to really get into that crazy, new, uncomfortable space. So with that, I hope that I can sell you on maybe some small ways to get started, to get kids thinking about these tough questions and being in these tough places. If I can ever help out and point you to anything, please feel free to email me. But I really appreciate your time, and I hope we can do some really cool things for the next generation of scientists. Thanks so much.